Good morning, everybody, and it's a pleasure to have some of the dignitaries here to speak for the morning session. The first speaker is Professor Srinivas. So he's a mathematician working for decades with distinguished works. He's also fellow of various academies, recipient of Bhatnagar Award. So it goes on, but I will hand over to him to start. Yeah, thank you so much.
We're told to be brisk, so let's try. My topic is on something which is sort of very forward-looking. What are the Bloch-Beilinson conjectures? If you came to Kapil's talk yesterday, both those names were mentioned, so I'm going to elaborate on that. Kapil said, I'll do various things in my talk today. I'm not going to do those things, but I'll do related things. So let's start with these two formulae. They look kind of strange if you've never seen such things before. The sum of all the positive integers is minus 1 over 12. And the second formula says the sum of the squares of the positive integers is 0. This is stuff which appeared, for example, in the writings of Ramanujan. And various people didn't understand how to interpret it, but of course the right people knew. And this is the explanation in mathematics. You have something called the Riemann zeta function, which is this series, sum of the powers, sum of the reciprocals of powers of n. Okay? If you took a calculus course, you would have taken S equal to P in India at least. At my time, summation 1 over n to the P, you would study convergence and divergence. That's the first series you would study in a math class. Now, S is a complex variable. For S large enough, this is convergent and it defines a function. But if you put S equals minus 1, it doesn't make sense, the series, but you'd get that series 1 plus 2 plus 3 formally. And you put S equal to minus 2, you'd get the sum of the square, and so on. So what Ramanujan is really saying, or others along with him, is that they're telling you something about the values of this zeta at negative numbers. So the way that works, Riemann is the person who understood this well, and Ramanujan rediscovered this. If you take this zeta and multiply it by S minus 1, this new function extends to a function across the entire complex plane with no singularity. What's called an analytic function, and it satisfies this symmetry. So if you give S a negative value here, I can compute 1 minus S, there is a positive value, and therefore I can compute this value in terms of that value. That's basically what Ramanujan is doing. He knows the answers on the positive side, and he's figuring out what happens on the negative side. There were those extra factors, they involved this thing called gamma, the so-called Euler gamma function. It's given by this integral, but it satisfies this recurrence relation. So from the recurrence relation is just integration by parts from that formula. That's easy enough from calculus. I compute that gamma at integers, positive integers, satisfies gamma of n plus 1 is n factorial. So in fact, gamma is some kind of generalization of the factorial continuous generalization. That's what Euler used it for, sort of, you can say. That leads to those formulas. Zeta minus 1 is minus 1/12, zeta minus 2 is 0. And in fact, similarly, you are able to use the same thing to show zeta of minus 2m is 0. Zeta of negative even integers is 0. And zeta of negative odd integers is a rational number given as coefficients in some expansion, series expansion. These are results of Euler, basically. So, by the way, some of you might have heard of something called Riemann hypothesis, and you might vaguely know it talks about the zeros of the zeta function. Well, here are some zeros, but these are what are called the trivial zeros. The Riemann hypothesis is about the other non-trivial zeros. These zeros everyone understands very well. So they're sort of not a difficult thing. Okay. Now these Bloch-Beilinson conjectures, whatever they are, and certain refinements due to Bloch, Otto, and so on, attempt to relate two kinds of data associated to what are called algebraic varieties, which is one term I have to explain more, and which are defined over algebraic number fields. I was a bit amazed that Kapil expects his audience to be very educated. He just wrote the terms down and expected everyone to know. I'm going to try and explain a little bit what they are. Let's see. Associate those things, whatever they are, there are two kinds of data, and the conjectures relate the two data. And it's not obvious to start with there should be any relation, but that's what the conjectures are about. One are the so-called orders of vanishing and special values of zeta functions and generalizations called L functions, like the Riemann zeta function. And the other things coming from geometry, what appeared in Kapil's talk, the so-called cycles in Chennai, those cycles, higher Chow groups, etc., which are defined using algebraic geometry and algebraic K theory. And the conjectures are supposed to explain why such formulas are correct. By in general saying there's a pattern, there are these two types of data and they're equivalent in some fashion or they're comparable in some way. And one reason for my own interest in these things, this is really number theory, I'm more of a geometer, but or algebraist. It turns out this has impact all over the place if it's correct. I want to state an elementary problem, well, at least at the graduate level in algebra. Let ABC be three complex numbers. If you take a polynomial vanishing at the point ABC, thinking about a point in 3 space, it's always possible to write the polynomial as a polynomial combination of the three linear polynomials, x minus a, y minus b, and z minus c, given by the coordinates. This, for example, you can expand f in a Taylor series around the point ABC. There are only finitely many Taylor terms because it's a polynomial, and then you gather the terms suitably. There's no constant term. Every other term is divisible by one of the way things. So this is obvious. I want to do something a little different. I want to assume my point ABC already satisfies some other polynomial. So this one, for example, x to the 37 plus y to the 37 minus z to the 37 equals 0. That's a specific polynomial of high degree. And assume ABC satisfies that. Can I do the same thing then? For which ABC can we find two other polynomials? So this is given to me, x to the 37 plus y to the, I'm given this equation. And then I want to find two other things, g and h, so that any f vanishing at ABC is now a combination where one of the polynomials used is this complicated one, rather than those three linear things. The linear things I did Taylor's theorem, here who knows, right? So this is the question. Basically, if you ask to guess, you'd say it's impossible. It will never happen. There's no way I can cancel off those high degree terms. Geometrically, the condition means that if you took the second two polynomials, which you started with ABC, then you asked to find two polynomials g and h, right? That was the problem. Sorry, let me go back a bit. My problem was to find these two things, g and h. So g and h are each define a surface in 3 space. Together they define a curve. That curve intersects the original complicated surface exactly at ABC and the intersection is transverse. This is what it's saying geometrically. It's virtually impossible, you'd think. You have a high degree polynomial, you're going to get many, many intersections. Usually you'd expect the number of intersections to be divisible by 37. If you give values of y and z, there'll be 37 x's satisfying it, right? So you expect it's not easy. And anyway, I just took 37 to make it concrete. I could have taken a large prime number, 2 to the power 11213 minus 1, for example, which is the largest one which was there when I was in school. Now the numbers are many more, but I can't remember. Anyway, at the end I'll say something about why it's related to those conjectures in number theory. And the answer, I'll give you the full answer for that concrete problem. It's not the empty set. In fact, it's a dense set of points, strangely enough. Okay, now let me try to discuss the inputs from algebraic geometry. If you like, I'm reviewing things which Kapil already did in his lecture. So the basic objects of study in algebraic geometry are what are called algebraic varieties. You have two types of them usually, and others more complicated ones. Affine varieties and projective varieties, we have two types of these things. They are defined as solution sets of finite systems of polynomial equations. So the question is, where do you take the solutions? Depending on that, you get affine or projective. And for the projective varieties to make sense, you have to have special kinds of polynomials, so-called homogeneous polynomials. So I'll elaborate a bit on that. Let's take the example which I took earlier in my algebra problem, x to the 37 plus y to the 37 minus z to the 37 equals 0. That's a polynomial equation. It defines some set. It defines a set in 3 space, it's a surface. But at the same time, it's a homogeneous polynomial. All the terms occurring have the same degree 37. So if you have a solution, I think of it as a vector in 3 space solving the equation, any proportional vector solves the same equation because all the terms have the same degree, that constant of proportionality will pull out, right? So the solutions are a union of lines, multiples of vectors. So the real information is not the actual solutions there for things like this, but sort of the parameter space of lines which arise in the process. So that's what projective geometry is about. And I just elaborated that. So there's a nice picture in a standard textbook in algebraic geometry which appears on page 12 of the book, so it's pretty basic. You could take an equation in 3 space, but it's homogeneous, so it will define on the one hand a surface, but which is a cone of lines. And on the other hand, it defines another thing which is a kind of curve, if you like, a kind of base of the cone in the projective plane, which is somehow at infinity. So you think of a light source at this point O, think of some body sitting in space, it will throw a shadow at infinity, right? the space in which those shadows live is the projective space. And for various reasons, algebraic geometers have realized that projective space is better than affine space for various reasons. The geometry is better. It's better to understand the geometry. Just to give you an example, you might have heard in the projective plane there are no parallel lines. Let me explain why that works. If you have a line in the projective plane, that's a line in this space, it corresponds to something which is a plane in 3 space through the point O. So if you have 2 lines in the projective plane, you have 2 planes in 3 space. But both of them contain the point O. So there's no chance those planes are parallel. I've started with a point common. Once 2 planes have a point in common, they're not parallel. There's in fact a line which is parallel, which is common, just from linear algebra. That line would be a line through O. And so that's a point in projective space. So any 2 lines intersect. Things like this. Projective geometry is better for various reasons. And for those who don't want to get much else from the talk, this is something you can look at. It's a website, imaginary.org. It has a gallery of pictures. There are 2 of them. There are huge numbers of these things. They've plotted all sorts of nice artistic shapes which you can use for various purposes, which come from algebraic geometry. This is a polynomial equation in 3 variables. This is another one. So each of them defines a surface in 3 space. They've plotted the real solutions. Of course, for algebraic geometry, you should really work with the complex solutions. Okay. Now, let me stress again, I'm dealing with algebraic varieties over C, but at the same time, defined over an algebraic number field is what I put in quotes. I'll take that to be the rational numbers for most of my talk. What that just means is that the defining polynomials, after all, an algebraic variety was the solution set of a system of polynomial equations. Those equations have coefficients. To start with, those coefficients might be complex numbers, but I can take the special case where those coefficients are integers, like x to the 37 plus y to the 37 minus z to the 37. That has integer, all coefficients are 1 or 0. For example, that Fermat conical surface is such. So then I can look at points with rational coordinates, point with integer coordinates. I can look at solutions of divisibility of values by prime numbers. I can do other arithmetic kinds of things once it's defined over the rationals. So in algebraic variety X, in the affine n space, we just use this term affine n space for the complex n space Cn to emphasize its algebraic properties, or in the projective space is called called a non-singular variety if it's a differentiable manifold in the sense of calculus and differential geometry. This I can't really explain in a half-hour talk. In an hour talk, I might have made an attempt, but not here. But basically, it just says near each point is a good system of local coordinates. But those coordinate functions might be analytic functions and not algebraic. Algebraically, you can't find local coordinates. And in the projective case, that has some implications for the topology. People who've been exposed a little to topology, for example, people like string theorists and so on who've seen some of these things, you know that the cohomology of a compact manifold, a compact oriented manifold has special properties. You have Poincare duality and you have things like that. So algebraic varieties would be examples of such things. Now, let X be one of these non-singular complex algebraic varieties. Associated, I can find certain groups which reflect properties of the geometry, and the groups depend on 2 integer parameters, P and N. Both are non-negative integers. So it's a bi-indexed family of groups. And these Bloch, Beilinson conjectures will use these groups to formulate them. I won't give the precise definitions. Kapil made some attempt at that. I'm not going to seriously try. But a generator is some kind of formal sum of parameterized families of subvarieties Z, T, and X, where the parameter space, the T, runs over an n-dimensional space. And the dimension of the total family is the dimension of X cross Cn. I have X, the original space, N, the extra parameters. Take this space and then it should have dimension P less. So it's sort of cut out by P equation, you can say. So that's the way the 2 parameters appear. I can keep increasing the number of parameters. I can keep changing the number of equations. Right? I can do 2 things. So that leads to 2 types of sort of cycles, as they're called. And then they have some relations imposed from the next higher dimensional things, families. And if n is 0, we're just considering there are no parameters. I'm just considering the original space. This is what actually appeared in Kapil's talk, cycles in the space X itself. And then the relations come from 1 parameter families. So that's, if you've seen any topology, there's a notion of homotopy, or there's another notion of cobordism, as they call it. You have, if you have a cycle inside X cross a one parameter space, then for each value of the parameter, I have a cycle, so I have a family of cycles varying in some fashion, and I can take two particular members and say this is equivalent to this in some sense. I can impose such relations. That's what you get for n equals 0. And those groups were studied earlier by Chow, was one of the people who studied them first, so they're called Chow groups in the literature. But these new ones with extra parameters, they also have some importance, and Bloch was the person who realized that. He called them higher Chow groups. And in IMSC, you do have an expert on higher Chow groups. Jaya Iyer has done work on that, so if you want to find out more, she can tell you at length. So if the variety X happens to be defined over Q, Beilinson showed how to define a subgroup of what you can call elements with integral coefficients somehow. I don't want to, again, elaborate, but there's a good way of defining these, which extends an earlier definition for n equals 0 where there was no problem. Beilinson had to be pretty imaginative to figure out what the right definition is here for this group in the higher case. And the group depends already on conjectural statements. There's some famous problem in algebraic geometry called resolution of singularities. And then there's the more nasty version of it, resolution of singularities in arithmetic context, where sort of the prime numbers also enter into it. Arithmetic resolution of singularities, if it's true, is one of the things Beilinson needs to use to define his things. He also needs to use the machinery of algebraic K theory, which is a kind of complicated business. I've written a book on it. It's 200 pages long. It's not so simple. Anyway. But the first non-trivial case, by the way, of this arithmetic resolution was actually proved by Abhyankar. That's one of his famous theorems. So there is an Indian contribution. The next case has also been done a few years ago. Abhyankar did the thing long, long ago. The next progress was only about 4 or 5 years back. And beyond that, we haven't gone. Okay, the first conjecture, this is not yet Bloch-Beilinson, just says all these groups which were defined by these various people are in fact finitely generated. Okay, it's a natural conjecture. Things coming from number theory have some sort of finiteness properties. But what do we know about it? Case p equal to 1 for the classical Chow groups is correct. This is something called the Mordell-Weil theorem for abelian varieties. It's a standard theorem in a graduate course in number theory, in arithmetic geometry, I would say. It's not an easy theorem, but it's understandable by a graduate student with some effort. Finite generation is essentially not known in any other non-trivial case. And particularly where n is positive, if x has positive dimension, unless you have some reduction to reduce to earlier cases, there's no non-trivial evidence at all. Even the case of dimension 0 is correct, but the proof of finite generation due to Quillen, essentially part of his Fields Medal citation, uses Raghunathan's theorem on finite generation of cohomology of arithmetic groups, one of the difficult theorems. So that's the case where the space X is a point. X of higher dimension we are far from touching right now. Okay, the Bloch-Beilinson conjectures in addition will tell you not only it's finite generated, it will tell you what the rank is, what is the essential number of generators. And it will tell you I can predict that essential number using number theory, using L functions, whatever they are, which I'm going to explain further. I'm going to tell you a little bit about what they are. And in the very special case where X is an elliptic curve, the P there is 1, N is 0, so it's a classical Chow group. This is the conjecture of Birch and Swinnerton Dyer. So this is really, really much, much more general than Birch. We have, somebody's offered $1 million for that very, very, very special case, and the conjecture is taken all spaces, all dimensions, all n, right? So somehow the way I like to see it, the conjectures are very forward-looking in this spirit, with apologies to Captain James Kirk. I don't know how many people in the audience have encountered Captain Kirk, but anyway. Well, the basic example of an L function is the Riemann zeta function, which I told you was summation 1 over n to the s. But it's also the product over prime numbers of 1 over 1 minus 1 over p to the s. This is basically saying that every number n can be factorized into a product of powers of primes. Now, if I write an infinite series, and I tell you each term can be factorized, I have the possibility of factoring the entire infinite series. Maybe. It depends on how the factorizations of the respective terms match up. So in this case, I claim they'll match up in such a way that the series will be a product of series 1 for each prime. And then each prime series will be just a geometric series, so I'll be able to sum it up and get Euler's formula. And in general, the L functions which I want to consider will have a similar product expansion, so-called Euler product expansion. By the way, very quickly, let me just say, because of this product expansion, you can see that there are infinitely many prime numbers. If there were only finitely many prime numbers, this is a finite product, so I'd be able to put S equal to 1 here. Then I'd get that the series summation 1 upon n is convergent, but we know it's divergent, so this is a contradiction. So this is a proof that there are infinitely many primes. You may say, I can find much simpler proofs. But the point is, this proof generalizes in various contexts. Dirichlet proved infinitely many primes in arithmetic progressions by generalizing this argument. The classical argument due to Euclid or whoever doesn't work, as far as we know. Anyway, so what are these L functions? What are these LPs? I'll first give an example. There's a kind of concrete way of writing down, but there's no motivation whatsoever. I pulled it out of the blue completely. Start with what's called an elliptic curve, which is y squared equal to a cubic polynomial in x. This is a curve in the plane with two integer parameter coefficients a, b. So this is one of these defined over q. And I'll take advantage of the fact that I can talk about divisibility. I'll let x and y range over the numbers from 0 to p minus 1. So the p squared choices of the pair x, y. And ask how many times is the value of the polynomial divisible by p. I can get different remainders. 0 is one of the possibilities. There are p of them. If they're randomly distributed and they're p squared choices, there should be p times it should happen. So let's look at the deviation, ap, which is p minus np. And use these aps to build an L function. Lxs is product over p of so-called good primes, 1 over 1 minus this ap over p to the s plus p over p to the s squared times product over p bad prime, something I don't tell you what it is, but whatever bad is, it divides this number. So there are only finitely many bad. And I've written an explicit formula for which are the bad ones. And there's also some formula, but I won't tell you what it is. Well, the general L is, okay, this is L. Fine, I wrote something down. Why should, it's not obvious this is interesting. It's clearly doing something, but anyway. But the general definition brings in things with topology and so on. So you can associate such an L function to each cohomology of the space X. The non-singular projective variety X I started with had these cohomologies because it also had an underlying avatar in algebraic topology. So the L function will have this form, product over P a good prime, LP of the ith cohomology at S times P over bad primes. Bad primes I won't touch, there'll be finitely many. But the good factors, you can say something, they'll have this special shape. LP HI XS is 1 over F sub P, the polynomial depends on P, evaluated at 1 over P raised to S. Let's go back quickly. That's how this formula looks here, right? This is 1 minus something times 1 over P raised to S times plus something times 1 over P raised to S squared. That's the general shape. And the zeta function itself has a similar shape. So for the L function of the elliptic curve, I'd take this polynomial. For the zeta function, I'd take that polynomial. And then I'd get back the formula which I wrote earlier. So what's this polynomial F sub P? It's based on Deligne's proof of the so-called Weil-Riemann hypothesis, which is one of the things for which Deligne won the Fields Medal. And it's also involved in this proof of the famous Ramanujan conjecture. People have heard lots of talks, including in this auditorium, on the Ramanujan conjecture. That proof of that conjecture constructs those polynomials as part of the business. And a conjecture of Serre then from 1971 predicts that these L functions satisfy properties similar to Riemann. So L HIXS will be a simple function involving gamma and so on times L of HIX I plus 1 minus S. And Serre gives a recipe for telling you what is a simple function and what are the bad, what to do with bad primes, etc., etc. Again, a longer talk, I might have tried to elaborate a bit, but there's no point. This is enough for this side. And for zeroth cohomology, which is the cohomology of point, I get Riemann zeta back. And for the top cohomology, we know again, reasons of Poincare duality, it's not very different from a point cohomologically, so I just get zeta shifted. So the new things are the other cohomologies. So a curve has only an H1, an additional cohomology. An elliptic curve has H1 with Betti number 2. That's why I got a quadratic polynomial. Right? That was the point. The degree of the polynomial is the Betti number coming from topology. The number theory and the topology are very deeply intertwined. That is somehow the thing coming out of all of this stuff. And I'm saying the algebraic geometry is intertwined as well. That's what Bloch, Beilinson is telling. Okay, Serre's conjecture is known in a few modular situations. For example, Wiles proved it. Basically proving that implies Fermat's last theorem. This is the main theorem of Wiles, that Serre conjecture is correct for the L function of an elliptic curve with semi-stable reduction. Now, what are the Bloch-Beilinson conjectures themselves? These forward-looking statements I talked about. So, they refer again to a non-singular projective variety defined over Q, and it will describe the behavior of all of these L functions near integer values of S in terms of the Chow groups. That's good. That's the sort of thing I wanted to explain. I had the Riemann zeta function at negative integers, and I said something about it, and I said I want to generalize that. But Riemann I just stuck to negative integers. Here too, the point is, using the Serre conjecture, if we believe the conjecture, only half the integers have to be checked. The other half will follow from the functional equation. So that's what we do. The conjecture is always better formulated on the negative side. So the first conjecture says, suppose m less than or equal to I plus I over 2 is an integer. Remember, bound here is I plus 1, but I'm going further. Then the order of vanishing of the L function at m is the rank of Chow, but at some other index, not m, I plus 1 minus m. And note that this is a positive number, and with a twist here, I plus 1 minus 2m. Note that this is also positive, because m is at most I by 2. Further, if n is this order of vanishing, there's an injective so-called regulator map, whatever that is, I won't again explain. The word regulator, I think, appeared in Kapil's talk, along with Abel Jacobi. Let it be there. Again, if you want more details, Jaya has written papers dealing as a regulator. She can tell you at length. It will take her a week to explain it, but I think it's possible to do it. The image is discrete, and the volume of the quotient torus equals the coefficient of s minus m to the n. Remember, we're saying the order of vanishing is exactly n. So the Taylor series starts here. There's a coefficient. It's telling you the coefficient is computed by the volume, co-volume of the regulator. So it's giving you really precise information, super precise information where we actually don't know, we have not proved anything. But anyway, note that m less than or equal to I by 2 means this twist there is strictly positive, which means we have a genuine higher Chow group. And the remaining cases where I is odd and where m equals I plus 1 by 2 is an integer. So I is an odd number, 2m minus 1. This involves the classical Chow groups. So there's a little extra thing. I have this rank which is supposed to be related to something. I break the rank up into two parts. The rank in topology, which is smaller in general, and then the difference. Let's just think of it like that. This is the topological rank, and this is the discrepancy. The hom there means it's something which is homologous to 0. Bloch-Beilinson conjecture part 2 says, suppose I is 2m minus 1, the order of vanishing of this L of an odd at S equals m is the rank of that discrepancy group. Further, there's something called a height pairing on that group, and the determinant, so in other words, you choose a basis here, this pairing produces a matrix of that size, take the determinant of that matrix, take the absolute value, and then that computes the coefficient of that Taylor expansion. And this particular conjecture, for x equal to an elliptic curve and I equals m equals 1 is exactly the conjecture of Birch and Srinivas, including the volume and Shah and everything. This was an earlier work of Bloch, by the way, showing that the traditional Birch-Srinivas is equal to this formulation. But nobody has proved it, huh? We just proved the formulations are equal. Then you can ask, what about that part you left out, the topological part? That also appears in number theory and comes from an earlier conjecture of Tate. The order of the pole of the L function of the even cohomology is the rank of that topological part of the Chow group, the integer Chow group. So it's an explanation. So what about evidence? There's very little evidence actually. An important evidence is the case where the dimension, the space is a point. I said finite generation followed from theorem of Raghunathan, later theorem of Borel, more precise actual computation of cohomology arithmetic groups imply this, the case of dimension 0. Then there are cases where BB2, for example, Birch-Srinivas is known in various cases, the famous theorem of Gross and Zagier and other things like that. And the main point is, if you look at the higher situations, there are cases where you can figure out what's happening on the L side, you can find zeros or whatever. Yeah, I'll be done quick. But people ate into my time in the beginning, so I have a little time. Typically, one knows the behavior of the L function because of modularity, and one has some elements you can write down in the Chow group. You compute everything numerically, and You want to say something is a rational number, you get 1.3333, you say if the computer found that, it's rational. Things like that. But there's no reason it should have been right, should have been some horrible thing. Instead, it's extremely regular. Many computations of that type have been done. No non-trivial example is known where BB says there's a certain rank and you can prove finite generation, let alone the actual rank in the higher cases. But the conjectures fit well with other conjectures regarding realization functors of mixed motives. This appeared also in Kapil's talk. What about my algebra problem? I wanted to quickly run over that. An algebraic number, let me just remind you, is a complex number which is a root of a polynomial equation with integer coefficients. So there are some sort of special numbers. They form this set Q bar inside C. And a concrete consequence of BB2 is in fact the following. If you have a surface in 3 space defined by capital F, X, Y, Z equals 0, and ABC is a point on that surface with algebraic coordinates, which is a special point, but there are lots of them, then any polynomial vanishing at ABC is always expressible as a polynomial combination where one of the polynomials is the same F, however complicated F is. It doesn't matter what the degree is. If the F has algebraic coefficients and the point has algebraic coordinates, it is possible to solve that algebra problem for this surface. We don't know this for a single polynomial, by the way. That's what the conjecture predicts, but we don't know this. Here's an explicit polynomial. It has lots of solutions, rational solutions. We don't know it for those solutions as far as I know. I expect if somebody claimed to prove, the paper would have come to me to refer it. Since I haven't seen it, I assume it's not known. Amalendu Krishna and I proved something of that which has that flavor. Let ABC be complex numbers, not 0, with A to the n plus B to the n equal to C to the n. N could be 37, for example, where n is at least 4. Then there exist polynomials GH such that any polynomial ABC is expressible where one of them is this, if and only if ABC is proportional to a triple of algebraic numbers. And proportional is okay. After all, the solutions of a conical set are, unions of lines. So if something solves it, any proportional thing certainly solves it. So I'm telling you, those are exactly the solutions. Bloch Beilinson type things would predict something, that and only that are the solutions. Here's Bloch. So many of you have seen him. He's even probably lectured in IMSC. Beilinson, I don't think he's been to India. Thank you.
Thank you very much, Professor Srinivas. We have a small memento for you from the Institute.
Thank you.